pick up where we left off on Friday. On Friday, we introduced what a distribution is, and today we will discuss the various operations we can perform on distributions. So to recap, from Friday, we saw that a distribution maps test functions to real numbers, and it's basically a functional that acts on this test function space that's linear, continuous, and finite. That's what we went through on Friday. And today, what we're going to do is see what else we can do with distributions. In particular, we'll discuss three operations, namely derivation. What's the derivative of a distribution? Multiplication. How can we multiply a distribution with a function? We often want to multiply two functions together, get another function. We'd like to do the same kind of thing with distributions. And composition. Similarly, we often want to take a function of a function. We might want to take a distribution of a function. And let's see, how can we make sense of these operations when we have distributions instead of functions. Then in the second part of the lecture, we'll discuss some applications to functional derivatives and Green's functions. And the Green's functions discussion will be very brief, but both functional derivatives and Green's functions are, in a sense, more naturally thought of in terms of the language of distributions, because the result of taking a functional derivative of a function is not always a ordinary function. It's often a distribution. And similarly, the solution for finding a Green's function for some differential operator, it's not always actually a function. It's often a distribution, which you might expect based on the delta that shows up on the right-hand side of that equation. Equation L G equals delta. Okay. So that's where we're going. Before I continue, are there any questions from last time? Is everyone clear what a distribution is? Okay. So our first operation we want to perform on a distribution is we want to take its derivative. So, well, we all know how to take a derivative of a function. Many distributions are functions, so the first thing we might want to try is just to use the usual rule. But I put a question mark here. It may or may not make sense for all distributions. Can anyone tell me why it does or doesn't?
They're functions of other functions, which means this epsilon is not one-dimensional, to say at least. So we wouldn't know how to move a slight bit in the space of functions.
That's right. So if u is an ordinary function, it makes sense to write u of x plus epsilon. Ordinary functions have well-defined values at each value of x. Distributions don't in general. So this is not going to work. This is basically going to be a dead end. As you pointed out, we want to always think about distributions as acting on test functions, and avoid, whenever possible, thinking about their values at particular points. So this is not a good way to think about it. This is basically a dead end. So we won't pursue this further. But we can, again, take inspiration from those distributions that are functions. So let's suppose we want to take the distribution, the derivative of a distribution that is a function when it's acting on a test function. So if u is a function, then this expression makes sense. So ordinary functions that are locally integrable induce functions by this map. So if this is a function, if u is a function, this makes sense. And if we have this expression, we can manipulate it further and try to get it to a form that makes sense even if it was not a ordinary function. So there's only one possible thing we can do with this expression, manipulate it, which is what?
Integrate by parts.
Integrate by parts, exactly. So if we integrate by parts, we get this. And so this first term we can simplify since our test functions have compact support. So phi vanishes identically outside of some finite region. So it's 0 at plus and minus infinity, and it's identically 0 in that region, so it goes to 0 faster than whatever u does. So this term goes away. Compact support. And we're just left with this term, which we can repackage as minus u acting on phi prime. And phi prime is always a test function because our test functions are continuous with infinitely many derivatives. So this expression, even though we derived it assuming that u is a function, we can just take this as a definition, even if u is a distribution that's not an ordinary function. So we'll take that as our definition. This is the definition of it's known as the weak or distributional derivative. And we can do this as many times as we like. And we just get factor minus 1 to the n, and derivatives acting on the test function. And this is one of the reasons we chose such a restrictive test function space, all these derivatives exist. So we can take as many derivatives as we like of our distributions. If we had a put weaker restrictions on our test functions, then we might have to stop at some point. Okay. So let's look at a couple examples of how this works. So the first example, you might be able to guess the answer. We'll look at a more involved example, and then you'll do an example a bit later. So first example will be Heaviside function, which is just the step function. It has a unit step at the origin. It's locally integrable, so it induces a distribution. Nevertheless, it has a discontinuity at 0, so it doesn't make sense to take its derivative using the definition of derivative you learned in your first calculus course. But we can take the weak derivative of this function. And we can do that just using the definition of the weak derivative. So that tells us that derivative of theta acting on a test function is minus theta acting on the derivative of the test function, which is the integral of theta times the derivative. With that, we can simplify because theta is just identically 0 for x less than 0, so this integral reduces from the integral from minus infinity to the integral from 0 to infinity of phi prime of x dx. And that's an integral we can do just using the fundamental theorem of calculus. So we just get minus phi of infinity minus phi of 0. Phi of infinity and is 0 because of compact support. You should get phi of 0 or delta of phi. Because these manipulations worked for any test function phi, we conclude that the derivative of the Heaviside function is the direct delta, as you may have been able to guess. Any questions on that? Yes.
If we have a much broader definition of test functions, does this still hold, but it's just much harder to show, or does it not even work anymore?
So the existence of the weak derivative depends on the existence of the derivative of the test function. So if we choose a test function space where the test functions are not differentiable, then at least in general you can't define the weak derivative. So this would just be undefined, as it is in ordinary calculus. Like if you try to use calculus 1 rules for differentiation and for this function, it doesn't make sense. And if you choose a sufficiently weak conditions on your test functions, then this more powerful definition of derivative will not help you. So you need enough. You need differentiability in particular. And note that this will agree with the ordinary definition of the derivative when both exist. We basically just use this integration of parts trick. Okay, so let's look at a slightly more involved example. Try to compute the derivative of this distribution. The first problem we encounter is that this function, the log of the absolute value of x, is not locally integrable, because the integral from 0 to a of this diverges. So in order to even define what this weak derivative is, we first need to define what we mean by the distribution ln of x. And what is typically meant by the distribution ln of x is that its action on a test function is the limit as epsilon goes to 0 of the integral of the test function times the log of x with a small region around 0 chopped out. It's a problematic region that prevents log from being a locally integrable function. And this is a definition. And so with this definition, we can then use our rule for the weak derivative to compute the derivative of this distribution. And what we get is minus the limit, so epsilon goes to 0, and so this should look familiar from tutorial, at least part of it. Well, at least in one more line. So from this point, there's basically only one possible thing we can do, as we'll often find in these manipulations. And as before, that's integration by parts. So we don't know really anything about the test function, except for the fact that it's continuous and differentiable and it's compact support. So if we want to evaluate this, we need to bring the derivative back onto the other part. We do that integration by parts. We get two terms. The first of which should look familiar from tutorial. This is just the principal value distribution. And then we get the boundary terms, which are phi of epsilon, log of epsilon, minus phi of minus epsilon, log of epsilon. So this first term, just the principal value distribution acting on phi. And the second term these boundary terms, well, we can do a little bit more work. So this is approximately 2 phi prime of 0 times epsilon log of epsilon for epsilon small. Here we've got 5 epsilon minus 5 minus epsilon. That just gives us twice the derivative times epsilon, which goes to 0 as epsilon goes to 0. So this part goes away. And derivative of the log is the principal value. With this particular definition of what a log distribution is. Any questions on that? Okay. So next, our next operation that we can perform with distributions is multiplication by a function. And the natural way to try to define multiplication of a distribution by a function is we can take inspiration from what we did before. So we know a huge number of distributions that are functions, and we want our definition of multiplication to agree. So let's take have one of those cases in mind and see if we can come up with a definition that makes sense even when our distribution is not an ordinary function. So let's suppose we've got a function psi. And we want to multiply it by distribution u and act with that on a test function phi. And so if u is a function, then psi times u is also a function. So we can just define this to be psi of x, u of x, phi of x, dx. This is okay if u is a function. And, well, it's even easier this time than it was for derivation. We can just multiply psi and phi together. And then what we've got here is the action of u on the function psi times phi. So we can define u psi times u on phi to be u of psi phi. So we'll take this as our definition. And this works in general. So I don't watch a lot of TV, but I think there's a channel about multiplication of distributions with functions, something like the Sci-Fi Channel. For this to make sense, what we need to check is that psi times phi is a test function. And if, well, so what conditions will we need to impose on phi for that to be true?
Continuous?
Continuous, yes. So we want psi to be continuous. Is that enough?
Compact support.
Continuous. Compact support. So compact support would certainly ensure that this is a test function. Is it necessary?
Because the other one has compact support.
This is compact support, so
We do need
it doesn't have to be. So be continuous, but is that enough?
All the derivative.
All the derivatives. It should have derivatives too. So continuous with infinitely many derivatives. So this is the condition for our choice of test function space. Would this condition be changed if we considered a different test function space? Or does this work for every test function space? No, it doesn't. Why?
Well, if psi diverges faster than phi converges at infinity, and phi has not compact support, then it doesn't work.
Right. Okay, so the example that was suggested is, suppose we consider a test function space where these phi's don't identically go to 0, but just go to 0 sufficiently quickly, say like a polynomial or exponentially. We could come up with continuous functions that diverge faster than that. We were considering a different test function space. So this is the case for our test function space. But in general, we just need psi-phi to be a test function. Okay. So at this point, I'm going to give you an example to work out. So let's suppose we have the distribution delta, and we want to take its derivative and multiply it by the function x. Can you, using the rules of multiplication and derivation, simplify this and write it in a simpler way? So your goal is to simplify this. I'll give you a few minutes a minute or two to work it out yourself, and then I'll hold the class. So I'm going to put up 4 possible answers here, and like before, I'd like you to just hold up the number of fingers, whatever you think the correct answer is, and we'll discuss. Okay, so here are 4 possible answers. First is minus delta. Second is minus delta minus x delta. Third is 0. Fourth is something else. So you got an answer and it was one of these or something else, you just hold up that many fingers. Okay, so there is a split among the class. About half of you have one answer, half of you have another. So I'm going to give you another few minutes, find somebody who disagreed with you, and try to convince them. I think most of you have reached a consensus. So I'll pull you again. Please hold up your fingers again. option you think is correct? Yes, there's substantial agreement. And somebody, and 1 is the correct answer. Can somebody explain the reasoning? Yes.
So you can first put the x inside the test function.
Okay, so we have x delta acting on phi first.
Delta prime of x phi.
Very good.
You can then put the definition of integration, of derivative, sorry.
Okay.
X minus delta and the derivative in the inside. And in there you will obtain 2 terms and the distribution is linear in there. So, well, but you will obtain phi prime, delta of phi prime, and then minus delta of x phi. No, the first one was phi and the second is x phi prime. Yeah. And yeah, that one is gonna vanish because you have an x times a function. Okay.
Why does it vanish?
Because x evaluated at 0 is 0.
In the integral,
Oh, okay.
that's gonna be 0 times phi prime of 0. So it just,
Very, very good. So this is delta of this thing evaluated at 0. So x is 0, phi prime is finite. Yes, Betty.
With that logic,
Yeah.
wouldn't the 1 and 2 equivalent as well? Because in 2 we have x delta, which is also 0.
That's correct.
That's the correct answer.
These two are equal. I would say the first one is simpler than the second. Any further questions on that, Katie?
Why is 2 equivalent to 1?
Because x delta acting on a test function is equal to delta times delta acting on x times phi, and this is 0.
well, in what we're doing, delta is defining phi and x delta is defining x prime. So, well, it's not, they are not evaluated in the same test function. So.
That's right, but this is true in general. So in our derivation, we'd have a phi prime. Good.
Yeah.
Okay. The last operation I want to discuss is composition. And by now, you can probably guess what we're going to do. We're going to start with a distribution that is a ordinary function. If that's the case, then we can define u of f of phi as u of f of x integrated against phi of x. This works. U is a function. And as usual, there's basically only one possible thing we can do here, which is what? Change of variables. Good. So let's say y is f of x. And then we would get f of y phi of g of y, g prime, y, dy, where g of y is x.
U of Y.
Sorry, this is u. Yes.
It's U of Y, not F of Y.
Yeah. U. There we go. U of, sorry, U of y. Yeah. U of y, phi of g of y. Yeah, there we go. And again, this we can this makes sense as long as this is a test function. And this will be a test function if f c infinity and y equals f of x has a unique solution. So that for our test function space, this will guarantee it. That this is a test function, and then we can define. We can just take this bottom line as the definition of u of f phi. We can say u of f phi is defined to be u acting on phi composed with g times g prime. And so this will the definition. It's guaranteed to exist if we put these conditions on, because then this is the test function, at least for our test function space. It's sometimes possible to weaken these restrictions for specific distributions. And one case that will be important to us is composition of the Dirac delta with a function. So we compose.
Sorry, question. What about the limits of the integral there? Why do we say that they're infinity and minus infinity?
Well, so we're assuming that this has a unique solution for basically for all x. So f has to be a function that goes from minus infinity to infinity. So the formula will basically be the same as before. I'll write it in a slightly different fashion. Let's write it in terms of the derivatives of f instead of g. Where, let me explain my notation here. F of xi is 0, and delta of xi acting on a test function gives us the test function evaluated at that point. So this is a shifted delta. So what this formula is saying is that for the delta, we can allow solution. We can compose it with functions that aren't don't just go from minus infinity to infinity without ever having a maximum or minimum. We can allow local maxima and minima as long as, so the only restriction on the use of this formula is that f should have only simple roots. Otherwise, this denominator would blow up. And this is an extremely important formula. It will show up all the time. Particular, well, it's going to show up a lot, but one place that we're going to use it extensively is in the last part of QFT2 when we're discussing perturbation theory for non-abelian gauge theories. This formula and its generalizations will play a very important role developing that perturbation theory, basically discussing interaction of gluons. So remember this.
Explain a little bit more what you mean by only sometimes possible.
So for every distribution in our distribution space associated with the functions that are C infinity with compact support, we can define U with F as long as F is C infinity and Y equals F of X has a unique solution. Basically, F goes from minus infinity to infinity, so it passes through every point to map from R to R. Then you can always do that. For delta, we can relax the second restriction in particular. And so delta really only cares about what's going on near 0. So it doesn't care if it goes through, basically goes through 0 multiple times, as long as it doesn't. So this formula will still make sense, and it will still act as a. This delta composed with F will still act as a distribution on this test function space in that case. So we can show that this would be linear, continuous, and finite with only this restriction instead of these restrictions. These restrictions are necessary if you don't make any other assumptions about what U is. But sometimes you can do better. So in particular, this says that if we have F of X is X squared minus 1, we can use this formula and delta composed with F just give us delta of 1 over 2 minus delta minus 1 over 2. But if F of X is X squared, that is a double root. And delta composed with F is undefined. Does that answer your question?
It's clear why it works with the delta, but it's not clear why it doesn't work always.
Okay. Perhaps we can discuss more later. Fatih?
I'm just asking out of curiosity. If we have a non-simple pole, for example, in QFT, are there any ways to deal with it? Like if we have fx is equal to x squared inside the delta function?
Sometimes we'll run across problematic expressions in in QFT, our usual approach is going to be to use physical reasoning and understand where the problem came from, and cases where it shows up, that's the way I know how to resolve it. I'm not sure about extending this theory in a mathematically rigorous way, but we'll see examples later.
Because, for example, for fields, if there is no mass, then you can see those kind of functions inside the delta functions. So do you do something like assume there is an epsilon mass of the field and then that epsilon goes to 0?
We'll do things like that, yes. Okay. So next, we'll discuss briefly a few applications. The first will be to functional derivatives. And in David's course, I believe you've been taking functional derivatives just by considering small perturbations to a function. And what I'm about to explain to you, the method I'm going to explain how to compute functional derivatives, is entirely equivalent to that. The reason I'm going to explain it this way is one, first, it's very natural to think about functional derivatives as in the language of distributions, because many of them are distributions. And secondly, at least to me and to many students in previous years, this method makes it more clear what to do in the case when you're taking multiple functional derivatives and the first functional derivative is a distribution. It can be done either way, but it's often more clear to think about it this way. So what a functional derivative is, often what you did in David's course is, say you want to take the variation of the action, you'd get some expression. It's the integral of delta of s with respect to whatever you're varying with, say that some generalized position times the variation of that quantity. And so this thing here is the functional derivative. And it's useful to think about it as a generalization of the partial derivative. So we can imagine what the variation in some quantity would be if it depended not on it wasn't a functional, but instead a function of a large number of variables. So if we had a function of a large number of variables, the variation in that function would be the sum of the partial derivatives times the variation in each of the variables qi. So you can see just by comparing these two formulas, we have a functional compared to a function to many variables. What changes is we have functional derivatives instead of partial derivatives and an integral instead of a sum. But there's a very close analogy. And so based on this analogy, you might expect that the way you compute functional derivatives should be able to be formulated in a way that's more similar to the way you compute partial derivatives. And in fact, it can be using the language of distributions. So the way to formulate things in terms of distributions is basically we're going to take this delta qi our delta Q of t, and write it as epsilon times the test function. That's basically what we're going to do. So we're going to think about this as some small parameter times the test function. And in that way, write the functional derivative acting, which in general gives us a distribution, not an ordinary function, acting on a test function is given by a very familiar expression. It's just the limit of f of f plus epsilon phi minus f of f over epsilon. This looks very much like the definition of a derivative you're used to. Yes?
Just want to check, when you've written delta s here the first time, inside the time integral, should that be delta L, delta Q? Or is that okay as it is?
It's delta S. So both sides. No, that's correct. I think.
If you take the continued limit of the sum, you are basically integrating over time, because each variable is q at some point in time.
The units don't agree, for example.
Okay. So I believe that's correct as is. Okay. So this definition just tells us we can compute functional derivatives in essentially the same way that we compute ordinary derivatives. We think about things as distributions. And just give a quick example of how to use this. In a case where the first, where the functional derivative will give us a distribution that's not an ordinary function. So here's our functional. The functional takes as an input f and outputs the value of that function at some point x naught. And if we want to compute the functional derivative of f with respect to f of x, we just use our formula. And f of f plus epsilon phi will just be f squared plus 2 epsilon f times phi plus epsilon squared phi squared x naught minus f squared of x naught divided by epsilon. These cancel. So far, all I've done is just plugged in f into this formula. Got 3 terms from the first one, and this is the other term. And the epsilon goes to 0 limit. This last term vanishes. so what we get is just 2f of x naught phi of x naught, which we can write as a distribution, or we can write this in this integral form, so we can read off functional derivative just by rewriting this as an integral with a delta. And so this is the functional derivative. This works for any phi. And because of this definition, basically the properties of the functional derivative that you would expect based on this analogy with partial derivatives all follow. And so functional derivatives are linear. They have the same product rule that you'd expect. And they have a chain rule. I wrote these out in the notes. I'll put them again in the tutorial so you can reference them when you get a chance to practice this. But very briefly, that's how you can apply these ideas to functional derivatives. And if you ever get stuck using David's method, I suggest you go to this method. It should make things clear what to do. Any questions on this? Okay. You'll have a chance to practice that in tutorial. Okay, the last thing I want to, again, also just talk about very briefly are Green's functions. Before I do, while I'm over here, I just want to emphasize again this formula is extremely important. If you remember one thing from the first two lectures, remember this formula.
Sorry, can I
Yes.
comment something? Sam asked the question if there should be an L. Is it possible that this S on the left-hand side is a distribution induced by the function S? In the same sense that the distribution delta, which acts on a function, is different than the delta function that we handle inside of an integral.
That's right. Yeah.
So we could just identify this integral with a functional derivative, this distribution which corresponds to the thing inside the integral, right?
That's right.
That's where the difference in dimensions comes from, if that makes it clearer.
Like, for example, if you consider the example we just
happening.
looked at, so d big F by d small f, then you get f times delta. And naively, you would only expect dimensions of f, and delta has dimensions of 1 over x. Right? So the dimensions don't agree with our naive expectations.
So yeah. So a key point in doing dimensional analysis is, so we know that the integral of delta of x dx is 1. So the units of delta of x are 1 over x. So this is a key point to keep in mind.
That's different to the delta we're using here, right? Yeah. This is a variation.
That's a variation.
No, but it's just an example.
The delta distribution which acts on the S function phi has different variations.
Like going for something to have you need a spacing like delta to do this. Which we don't have, like we had it in the string case. We can do this.
Okay, so our final application of distributions, the Green's functions. This is a big topic, and I'm not going to say a lot about it. I'm mostly just going to give you a useful way to think about these things in terms of distributions and what are known as integral kernels that we'll talk a lot about in QFT2. I just want to introduce that idea. I'm not going to talk at all about how to compute these things. In some of the courses, we'll compute specific Green's functions. So what a Green's function is it's a way to solve a differential equation like this. So here L is a linear differential operator. F is a function, and we want to solve for y. And so this is very similar to problems we're used to dealing with in linear algebra. And the one way we'd solve an equation that looked basically identical to this, but with slightly different interpretations, is you could find, say, y is equal to L inverse times f. So if this was a matrix, these were vectors, this is how you would solve the equation. Just find L inverse. And the idea of Green's functions is basically doing the same thing, except for matrices. Instead of for matrices, but doing it for differential operators. And so this is the inverse differential operator. And I want to expand a little bit further on this analogy. So we can think about this problem involving differential operators and functions as like an infinite dimensional analog of the matrix problem of finding, having a matrix here, say an n by n matrix, multiplying a vector equaling another vector, and trying to solve for this vector y. So in the analogy, a vector v is analogous to a function f. Component vi is analogous to the value at a point. A matrix M is analogous to an operator O. Matrix element Mij is analogous to what's known as the integral kernel, and this may not be as familiar to you as some of the other things. So let me elaborate a little bit more on this point. So with the integral kernel, if you want to think about this equation as an infinite dimensional operator, then it's useful to think about vectors both in terms of their as an entire object and in terms of their components, and similarly for matrices. So for a function, the analogy is clear. We have a function, its value at each point is like a component. The label I is like the argument x. So there's infinitely many possible components. And so we want to do the same thing, have the same interpretation for a matrix. So let's try to take the matrix equation, or let's try to consider a multiplication of a matrix times a vector in terms of components. So what we would do there is multiply the matrix times the vector and sum over components j. That's how we would get the ith component of this vector that we get by multiplying a matrix times a vector. I'm going to take an operator, the analogous quantity in terms of functions and operators is we want to take an operator, multiply it by a function, evaluate at a point. To do that, what we would want to do is then integrate instead of sum the integral kernel of the operator, k, times the function dy. So this is the integral kernel of this operator, and it's often a distribution. And this is going to be a very useful way to think about operators and inverse operators, particularly in QFT2. We'll be thinking about things in this language a lot. And the identity matrix has the analog of the Dirac delta. So in terms of this analogy, we can think about the Green's function as the integral kernel of this inverse operator. So if we're going to write this, so what is L inverse? L inverse is an operator such that L inverse times L is the identity. The identity is the Dirac delta. And so this, let me write it in the other order, write it as L times L inverse. This equation, if we write it with arguments, basically is the Green's function equation. So if we write this out, Lx times g of x c is delta of x minus c. We can, in linear algebra, this would be the matrix equation. L times L inverse is 1. And functional analog, L times L inverse are operators. Their product is this distribution. We add the indices. It's like this. So the reason I said this is just an analogy is that there's sometimes subtleties over here. Usually involving the boundary conditions. Some of those may come up later in the year, but I'm not going to talk about them now. But what I just wanted to say about this is that using this analogy and keeping in mind that often these integral kernels, or generally most of the things on the right-hand side, are distributions, not ordinary functions. You can use your intuition from linear algebra in unfamiliar situations and usually get the right answer. Be aware that there sometimes are subtleties that we'll may discuss later in the year. And we'll see an example in tutorial this afternoon that will illustrate these ideas. So that's all I wanted to say about distributions. So just to recap very briefly, distributions are linear, continuous, finite functionals that act on a test function space. We can do most of the things we'd like to with ordinary functions. In cases where it wouldn't make sense, we can take derivatives of discontinuous functions, for example. And yeah, just one more time, I'd like to emphasize that formula. Don't forget that formula. That's all I wanted to say about distributions, and we'll practice some more in tutorial today, and then tomorrow we'll move on to something completely different.